Okay, thank you.
Thank you. Yeah.
Right.
All right. So we are going to the second talk delivered by the Professor Meng from Hong Kong Polytechnic University. And Professor Ni received his PhD degree in mechanical engineering from Hong Kong U in 2007. And after working as a postdoc researcher in the Hong Kong U, Professor Ni joined the Hong Kong PolyU in 2009, and then promoted to associate professor and full professor in 2016. And Professor Ni also served as associate head for 5 years, and he started to serve as associate dean of Faculty of Construction and the Environment in 2021. And Professor Ni's research interest include the fuel cells and rechargeable metal ion batteries. And particularly, he has developed a series of multi-physics models for fuel cells to optimize the electrode microstructure and stack configuration. So he also developed perovskite oxide for the use as the fuel cell cathode. Currently, previously he served as the associate editor for the Science Bulletin from the 2015 to 17. Currently, he is the senior editor for Sustainable Energy Technologies and Assessments, and associate editor for 2 journals, International Journal of Green Energy and International Journal of Energy Research. So today's topic will be the fuel flexible solid oxide fuel cells for efficient power generation. So without further ado, please join me to welcome Professor Ni. Professor Ni, please.
Okay, thank you, Professor An Liang, for your nice introduction. So it's my great honor to share with colleagues our research on solid oxide fuel cells using different fuels. So my name is Meng from HK PolyU. So I will first give you a brief introduction to the background of our research. Why do we choose to work on SOFC? It's kind of fuel cell, but it's working at high temperature. Then I will share with you our research on SOFC, including the cathode material development, the testing of fuel cells, solid oxide fuel cells using different fuels, and some engineering design on SOFC to improve the stack performance and durability. And in the end, some conclusions will be drawn. So, we are currently relying heavily on fossil fuels for energy conversion, including coal, oil, and so on. And in the coming few decades, fossil fuel will continue to be a very important energy resource. Fossil fuels are actually used in conventional thermal power plants for electricity generation. And we need to go through multiple steps in order to convert the chemical energy of a fuel into electricity. And this will involve a lot of energy loss. And the energy efficiency for conventional thermal power plant is thus about 40%. And it's very difficult to further improve. Since we have to rely on fossil fuel for some period, we need to think about, can we identify or develop some advanced energy conversion technologies to replace conventional thermal power plant so that we can improve the efficiency and reduce the carbon emission. Fuel cells are very promising for energy conversion, especially the high temperature fuel cells working at about 800 to 1000 degrees Celsius. They can very effectively convert the chemical energy of fuel into electricity through electrochemical reaction. So like many other type of fuel cells, like PM fuel cell or alkali fuel cell, the high temperature solid oxide fuel cell mainly includes 3 main components: the porous anode, porous cathode, and a dense electrolyte. So in operation, we supply fuel and air into the anode and cathode channel respectively. Then in the cathode side, the oxygen can be reduced to produce oxygen ions consuming electrons. Then the oxygen ions can be conducted from the cathode to the anode through the dense electrolyte. In the anode side, the oxygen ions can oxidize the fuel to produce water, CO2, as well as electrons. Then the electrons can be collected by the intercollector and flow through the external circuit back to the cathode to produce useful power. So this is the working principle. So as long as we supply fuel and air into anode and cathode, we can continuously produce electricity. And because, well, the energy conversion is very straightforward, through electrochemical reaction, not through a thermodynamic cycle. So the energy efficiency of a fuel cell, especially the high temperature solid oxide fuel cell, can be very high, can be over 50%. Because the working temperature of SOFC is high, so they are very suitable for stationary applications, especially for combined heat and power cogeneration. For example, this is the Siemens Westinghouse large-scale SOFC for combined heat and power cogeneration. Using natural gas, you can produce electricity, you can also produce hot water. And this is a small-scale, actually micro-scale combined heat and power cogeneration developed in Japan. They use SOFC for power generation. And the waste heat from the tank is used for hot water production, so that you can achieve a pretty high overall energy efficiency. If you look at their electric efficiency, power efficiency, well, you can see, well, it's over 53%. So it's very good. Apart from stationary applications, solid oxide fuel cells can also be used in electric vehicles, but it's mainly used for range extension. So SOFC tank is used to charge the battery, so that the battery can be used for longer period to give you a long range of electric cars. Although the SOFC are very promising for different applications, they are not so popular nowadays because of the relatively high cost and relatively poor durability. In order to reduce the cost of the SOFC system and to improve the durability, it's very important for us to reduce the operating temperature from very high, about 800 degrees Celsius to 1000 degrees Celsius, down to about 400 to 600 degrees Celsius. Because in a lower temperature, well, we have a wider material choice, so it's possible for us to use cheaper materials. And the thermal management system is also simplified. And the startup, of course, it will be faster compared with high temperature operation. And the lower temperature, the material sintering problem will be less severe. The thermal cycling problem is also less severe. So we can improve the durability by reducing the temperature. However, when we reduce the operating temperature down to about 400 to 600 degrees Celsius, the actual performance of SOFC will also be decreased, mainly due to the decreased ionic conductivity of the electrolyte, as well as the decreased electrode activity. So these two will increase the ohmic loss, as well as the electrode polarization resistance. And from the engineering design point of view, the fuel cell performance is also not optimal because there is a big gap between the nab scale button cell performance and the large cells performance. For example, for button cells, we can achieve very high power density, probably between 1 to even 2 watt per centimeter squared. But for large commercial scale cells, the power density is normally around 0.5 watt per centimeter squared. And this is mainly due to the unoptimized engineering design. So in order to improve the performance of SOFC and reduce the temperature, the solution is to develop new materials as electrolyte or cathode, because among the different components of SOFC, the cathode loss actually dominates the overall overpotential loss of SOFC. So the cathode is a key component. And another thing is to conduct engineering design so that we can optimize the electrode structure and the stank structure to improve the electrode performance and the stank performance. So here I would like to briefly share with you our research in the following 3 aspects. The cathode material development, since the cathode is so important. And we also did some testing on SOFC using different fuels. And we also conducted engineering design to improve the stank performance. So in our group, we have developed a series of perovskite materials for possible use as SOFC cathode. So here I just want to use probably 1 or 2 material as an example to illustrate what we have done. So this BCF perovskite oxide is quite promising SOFC cathode because this material shows a good oxygen ion conduction due to the enlarged lattice free volume. And the activity is also very good due to the variable valence states of cobalt and ions. However, on the A site is the Ba and the B site is cobalt or ion. Because the A site and the B site size difference is quite large, so this will cause low symmetry, and this will favor the hexagonal phase. So the cubic phase will not be favored due to the large size difference between A site and B site. And this phase, hexagonal phase, will increase the oxygen vacancy formation energy, which is not very good for oxygen ion conduction. So the solution is either to dope the A site with some smaller elements, such as the BSCF material developed by Professor Zhongping Sao, or replacing the B site with some larger ions, so that we can reduce the size difference between A site and the B site. Also, in the past few years, we try to dope the B site with some larger ions. For example, partly replace the iron with the Y ions, because the Y ion is much larger than iron. So we successfully transform the hexagonal phase into cubic phase, which can give us a much better electrochemical performance. So we conducted the ECR measurements, and we observed improved the oxygen bulk diffusion coefficient and the surface exchange coefficient. And we also tested on the area specific resistance of the different cathode materials. And you can see this new material, the BCFY material, showed the lowest ASR compared with some other commonly used cathode materials. So it demonstrates that the material is better than other materials. And using this material, we fabricated SOFC, and we tested the SOFC performance and the different temperature. And we achieved a very good power density, about 1,000 milliwatt per centimeter squared, and 600 degrees Celsius. So this is one type of material we developed. Actually, we also developed a few other perovskite materials, and based on our experience, we found normally the cobalt containing materials show much better performance than other materials. However, there is a problem for cobalt containing perovskite materials, because normally their TEC, thermal expansion coefficient, is high. For example, the cobalt containing materials, normally their TEC is about the TEC of GDC or YC. It's about 2 times the TEC of GDC or YC. So these two are common electrolyte materials. So due to the large TEC difference between the cathode and the electrolyte, then in the long-term high temperature operation, especially after some thermal cycling, it's possible that some cracks can be formed within the porous cathode and the interface between the cathode and the electrolyte, which will decrease on the fuel cell performance or even cause fuel cell failure. So it's very important to control the TEC of the cathode to ensure it's very close to the TEC of the electrolyte materials. So in recent years, in collaboration with Professor Zhongping Sao, we developed a new strategy for cobalt containing cathode materials by thermal expansion offset approach. Since the cobalt containing perovskite materials, such as the SNC, has a high TEC value, then we try to mix the cobalt containing perovskite materials with other oxides showing lower TEC value. For example, we selected YWO oxide, and this material showed even negative TEC value. So by mixing these two, we can well control the TEC of the composite. So these two figures basically show you that we can control the TEC of the composite cathode material by simply controlling the composition of the two different material. One is the cobalt containing perovskite material, another one is YWO, which shows negative TEC value. So you can see by controlling the composition, we can achieve a TEC value of this amount, which is very close to the TEC of the electrolyte material. So we use this material in the SOFC, and we tested the fuel cell performance, and we find actually the composite cathode material can not only give you much better performance, but also very good durability. This is because when we composite the two materials, we find some of the strontium atoms will be exhausted from the bulk of the cobalt containing material. So this will cause the A site deficiency of the perovskite, which will favor the oxygen conduction property. And this will decrease the polarization resistance of the material. So you will find using this approach, actually we can successfully decrease the RP, the polarization resistance. And in the long-term operation, especially after some thermal cycling, we heat up the fuel cell and cool down the fuel cell by about 40 cycles. And we find the fuel cell still work very stably. But using conventional copper-containing perovskite cathode material, you will find the polarization resistance is continuously increasing. So the durability is not very good. And then we look at the microstructure of the fuel cell after thermal cycling, and we find using the conventional cathode material, there we observed very clear crack between the cathode and the electrolyte, which will obviously decrease the fuel cell performance or even fuel cell failure. But when we use the new strategy, you will find there is no crack, right? And this explains why the fuel cell can perform so stably, right? And in the previous research, well, the strategy for us to develop new materials is basically based on the trial and error approach, right? We try to dope some elements into the A side or B side, and with a hope to improve the phase stability or to improve the activity. However, we find it's very expensive and very time consuming. So in recent years, we try to develop some advanced approach to facilitate material screening. For example, we developed the machine learning based approach, and we use machine learning to screen a lot of material, and then we can identify some potential materials. Then we fabricate the material, test the material, and then we can find out some very good candidates for use in SOFC. So recently we developed this approach, and we look at a few descriptors such as the ionic Lewis acid strength, tolerance factor, and so on, because these factors, these descriptors are widely used in the literature for material selection. So we first look at whether these descriptors are very important in terms of the area specific resistance of the material or not. Then we find actually the ionic Lewis acid strength shows the highest importance. In order to achieve the lowest area specific resistance, we find we need a low A site ionic acid strength and high B site ionic acid strength. However, when we look at the ionic radius, we didn't find a very strong correlation between the radius and the area specific resistance. So we believe the ionic acid strength should be a very important descriptor to help us screen materials. So we use the machine learning, deep learning methodology, and we screen over 6,000 materials. And eventually we identified a few very promising materials. Their composition are shown here, quite complicated. So we actually fabricated these materials, especially this one, SCCN for short, SCCN. And we test on the performance of this material, and we find the polarization resistance is really very low, and 700 degrees Celsius is only 0.0101. It's very good. Then we use this material in SOFC, and we test the fuel cell performance, and we achieved a very good fuel cell performance. You can see, and a temperature of only about 650 degrees Celsius, we achieved a peak power density of around 2,000 milliwatt per centimeter squared, and it's quite stable over 800-hour operation. So this material should be very promising for use as SOFC cathode. So that's a very brief sharing about the new material development. Apart from new material development, as an engineer, we are also interested in testing the fuel cell using alternative fuels, because compared with low temperature fuel cells, one advantage of solid oxide fuel cell is the fuel flexibility. So we can use different fuels in solid oxide fuel cell for power generation. So we tested carbon fuel in SOFC for power generation. The reason for us to use carbon is because carbon is the major component of coal, and the coal is a very important energy source in China. So if we can effectively convert coal into electricity using high temperature fuel cell, then we can provide an alternative approach for coal conversion, right, in an efficient and clean manner. So this is one reason. Another reason is carbon is also a main component of biomass. So if we can effectively convert carbon into power, then we can also effectively convert the biomass into electricity. So this is the motivation behind. And when we look at the direct carbon solar oxide fuel cell, we find actually carbon cannot be directly utilized in a fuel cell because the size of the carbon particle is quite large, about a few tens of micrometer. But the pore size of the porous anode is only about 1 or 2 micrometer. So it means the carbon particles cannot enter the porous anode, right? So it cannot be directly utilized for power generation. Actually, the carbon is utilized in an indirect way. So the carbon is first gasified by carbon dioxide to produce carbon monoxide, CO. Then this is gas, right? The gas can be easily diffused from the carbon fuel to the interface between the anode and the electrolyte. Then the CO can be oxidized to produce CO2 and electrons. And the CO2 can be diffused from the interface to carbon to gasify carbon again, right? So this whole process will proceed continuously, and the carbon can be continuously utilized for power generation. However, the fuel cell performance for this type of fuel cell highly depends on the carbon gasification, because this reaction determines the amount of carbon monoxide to be produced, and CO is the actual fuel for power generation. Because this reaction is relatively slow, in order to achieve a good fuel cell performance, normally we need to maintain the fuel cell at a pretty high temperature, for example, 850 degrees Celsius. And this is actually not very good, because if the temperature is too high, this will cause some durability issue, right? The sintering of the anode particles will be significant, and the thermal management will be complicated. So in the past few years, a lot of research work have been done to decrease the operating temperature from 850 degrees Celsius down to 750 degrees Celsius, but actually it's not very successful. In our team, in collaboration with Professor Liu Jiang from South China University of Technology, we actually tried something. So we try to add some catalyst into the carbon fuel with a hope to facilitate the carbon gasification reaction. So you can see when we add some catalyst into the carbon fuel, we can improve the fuel cell performance, but the improvement is not very significant. So we still need to operate the fuel cell at a pretty high temperature, 850 degrees Celsius. So it can work, but it's not sufficient. So in the past few years, we start to think about, can we adopt some engineering approach to solve this problem? Because in coal application, normally we use steam, use water vapor to gasify coal, right? Coal gasification is normally done by water, not CO2. Of course, CO2 can also gasify coal, but it's very slow. Then for the carbon fuel cell, we also think about, can we use water for carbon gasification? Then we did some theoretical analysis, and we find there could be two benefits using water for carbon gasification. First one is the carbon gasification by water can be much faster than carbon gasification by CO2. So this is one benefit. And using water for carbon gasification, we will not only produce carbon monoxide, we will also produce hydrogen. So both hydrogen and the carbon monoxide can participate in the electrochemical reaction for power generation. And you should know, hydrogen oxidation is much easier than carbon monoxide oxidation. That means this reaction will give you much lower polarization resistance. So using water for carbon gasification, we do have two benefits. One is we can enjoy faster carbon gasification. Another one is the activation over potential. The polarization resistance can be greatly reduced. So we did some testing in Nanjing, and we also did some multi-physics modeling. And we found when we replace CO2 by water, we can significantly improve the fuel cell performance. As shown in these figures, for example, for this one, the blue curve represents the fuel cell performance using CO2 for carbon conversion. And this red curve represents the fuel cell performance using water for carbon gasification. And you can see the improvement is very significant. Then we use the multi-physics model to understand why. And then we find using water for carbon gasification, the carbon gasification reaction rate is indeed much higher than carbon gasification using CO2. And using water for carbon gasification, the fuel for electrochemical reaction, the concentration of fuel for electrochemical reaction is also much higher, right? If you look at the different corner, you can see, well, the difference is very significant. So we look at on the direct carbon solar oxide fuel cell performance and a different temperature, and we find when we use CO2 for carbon gasification, indeed, we need pretty high temperature in order to achieve a high performance. For example, if we want to achieve a current density of about 3,000 ampere per centimeter squared, we need a temperature of around 850 degrees Celsius. But when we use water for carbon gasification, then the performance can be much improved. And when we reduce the operating temperature by 100 degrees Celsius, that means 750 degrees Celsius, the performance of the fuel cell is still comparable to the performance of fuel cell using carbon dioxide for carbon gasification. So it means, well, using water for carbon gasification is a very simple strategy, but it works. So this is some work we have done on direct carbon solar oxide fuel cell. And apart from carbon fuel, we are also very interested in using other carbon-containing fuels, for example, even with the plastics. So we try to test solar oxide fuel cell using the waste plastics. So the waste plastics is first pyrolyzed in a reactor to produce biogas. Then the biogas is directly supplied to SOFC for power generation, and we can still deliver a good power density using this fuel cell. Then we try to add some pyrolysis catalyst on the top of anode catalyst with a hope to significantly reform the biogas. And you can see, well, using the catalyst on the surface of the SOFC anode, we can significantly improve the fuel cell performance, right? The power density is increased very significantly. And recently, we are also working on SOFC using biogas as a fuel. A few years ago, I worked with colleagues from civil engineering department. They are working on wastewater treatment, and they can produce a lot of biogas. Then we try to use their biogas in SOFC for power generation. And we test our SOFC using biogas, and we find the performance is not bad. Of course, compared with hydrogen fuel, the power density is not that high, but it's still very good. Using hydrogen as a fuel, we can achieve a power density of around 1,100 milliwatt per centimeter squared. But using biogas, real biogas, we can still achieve about 900 milliwatt per centimeter squared peak power density. So this is pretty good. So apart from using SOFC for power generation with different fuels, we are also interested in engineering design, because as already mentioned, there is a big gap between nanoscale button cells and large-scale commercial cells. For nanoscale button cells with a surface area of about 1 centimeter squared, the power density can be very good, 1 to 2 watt per centimeter squared. But for large-scale cells with a surface area of more than 100 centimeter squared, then the power density is much lower, roughly around 0.5 watt per centimeter squared. So this is a typical planar large-scale cells, and normally we need to integrate multiple cells to form a stack in order to increase the voltage, to increase the power output. And this is the intercollector to collect different cells. And this is the rib of the intercollector. And you will find the intercollector geometry is very important in terms of the stack performance, especially the rib size. So this is the rib of the intercollector, because the rib size will determine the channel, right? Will determine the flow field. The rib size will also control the current collection. So in the past few years, we actually look at how to optimize the rib size and how to improve the stack performance. You will find the rib size is very important, because when the rib size is too small, then the current collection will be challenging, right? Will be very difficult. But the gas diffusion under the rib will be easier, right? Will be easier. However, if the rib size is large, you will find the current collection is easier, but the gas diffusion, especially the oxygen diffusion under the rib, will become an issue. So, so we think about how to solve this problem. So a few years ago, we tried to use metal foam to replace the rib of the intercollector with a hope to provide a more uniform oxygen distribution and the air and the cathode side. So here shows you some simulation results. So we find for the conventional design, we have the channel and the rib, right? But under the channel, you will find the oxygen concentration and the cathode electrolyte interface is pretty good. We have high oxygen concentration, but under the rib, so this is under the rib, you will find the oxygen concentration is pretty low because the oxygen diffusion under the rib is difficult. So you will find, well, for these areas, the oxygen concentration is very low. So the local cell performance is poor, which will decrease the average power density of the whole cell. However, when we use the metal foam to replace the rib of the intercollector, then we can provide more uniform oxygen distribution over the entire cathode, which can improve the cell performance. So based on the calculation, you can see using metal foam to replace the rib, we can successfully improve the power density of the large scale cell, right? So this is very successful. And more recently, my postdoc, Dr. Guomei also conducted some simulation simulation, and we designed some unconventional rib design in order to improve the oxygen concentration under the rib. So unlike those conventional design with continuous rib, we try to use desiccate rib. So the gas will be supplied in this way, and the gas can also flow in this way. So the oxygen concentration under the rib could be improved, right, by using the desiccate rib. And of course, we also designed a different intercollector configuration, and we did the simulation. So here, I just want to show you some selected results. So these figures show you the oxygen concentration and the cathode electrolyte interface. So this is the conventional design, and you can see the oxygen concentration under the channel is pretty high, but under the rib is very low. So this will cause a low average cell power density. However, using different design, of course, for these two designs, I think they are not very effective. But for the other design, like the case 4, 6, and 8, you can see, well, the oxygen concentration even under the rib can still be improved significantly, especially for these two figures, right? You don't see very low oxygen concentration. That means the whole cell can perform very well. But for the other case, when you see the dark blue color, it means the oxygen concentration is very low. It also means the local cell performance is very poor. So you can see using different design, we can improve the overall performance of cell by simply designing different intercollector geometry. And we found we can successfully improve the peak power density, and the increment of peak power density can be around 25% or even up to 30%. Of course, we also need to double check the pressure loss. And we find using the new design, indeed, the pressure loss could be increased, but it's not very significant. The performance gain is still much higher than the additional power consumption to overcome the pressure loss. So those unconventional designs work very well. So these are something I want to share with you. And to conclude, well, from what I have presented, you can see SOFC are very promising for power generation, especially for stationary application, and using new techniques such as machine learning, experimental testing, and DFT calculation. When we integrate the 3 different methodology, we can facilitate material development. And SOFC is capable of using different fuels for power generation. And the stack design is also very important to realize high performance SOFC stack and system. So this is the end of my presentation. And I'd like to thank my group members, my students, postdoc fellows, research assistants, collaborators, and funding support from different agencies. So thank you.
All right, thank you very much for your next talk, Professor Ni. So this section now is open for the questions. Any questions from audience? And you may text your question in the chat box or directly unmute yourself and ask questions. Yeah, I can go first. Okay, Professor Ni, I'm curious about the direct carbon solid oxide fuel cells. You mentioned that the particle size is around a few tenths of a nanometer, still large for the fuel
micrometer,
cell, right?
A few tenths micrometer. So
micrometer.
Sorry, maybe, yeah.
Okay, micrometer. So
Yes.
that my question is, if we really want to use the coal as the the fuel, so how to cut the coal into the a few micrometer?
I think we need to do some fuel processing. Yeah.
Oh, okay. Okay. All right.
Yeah.
Okay. 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 Thank you. Yeah.
Yeah. Thank you.
Any other questions from audience? No? Okay. Okay. Please join me to thank the Professor Ni again. Thank you very much, Professor Ni.
Okay. Thank you.
Okay, so I think we finished this section. And once again, please join me to thank Professor Shaw and Professor Ni again for their very interesting talk. Thank you very much. Yeah, now this section is closed.